random variables. We are not sure on the outcome of the event, right? If I want to purchase a particular stock, I'm not sure whether the price of the stock will go up in future or go down. Means there is a lot of involvement of probability in our investment decisions. So majority of the variables that we are looking at in our day-to-day life, they are all random variables. So once they are random variables, all I can make is only probabilistic statements about those random variables. I can only make statements subject to different probabilities because there is an uncertainty. So that is where if I understand the pattern of the probabilities, and that patterns are what are getting converted into different kinds of distributions based on probability. So once I understand the different kinds of distributions, I can try to map the behavior of my random variable with that appropriate distribution. So we'll talk about a few commonly used distributions in finance. Probably I can look at something like uniform distribution. We'll talk about something called binomial. We'll talk about normal distribution, a few of them which have a decent number of applications in the world of finance. We also look at the log normal distribution. These distributions, the understanding of them, they have lots and lots of applications in finance. The option pricing, the derivatives pricing models, they use a good, they make a good usage of these probability distributions. And even if I want to understand the statistical inference making, which is a part of inferential statistics to make conclusions based on the data, even there the understanding of the distribution become more and more useful. So that is where we should start understanding the concept of probability distribution so that we can map them towards the decision making process, right? So as a part of that, I think that we should look at the concepts which I am covering here. I would be covering a few discrete random variables, in fact talking about a couple of important discrete probability distributions. Then I'll spend some time in terms of understanding the continuous random variables and continuous probability distributions. A few of them are called as continuous probability distributions, a few of them are discrete. And towards the end, I would just focus on how we can generate these kind of distributions, right? How we can generate the data in case I don't have the data. How can I generate the data which is following a particular distribution? How can I generate the data which is following let's say binomial distribution? How can I generate a data which is following a normal distribution using a mechanism called Monte Carlo simulation? So these are the different topics that we will cover as a part of this particular session. So initially, let me get started off with the discrete random variables or discrete probability distributions. So once I know that a random variable is nothing but the outcome is uncertain for it. Whenever I talk about a random variable, if I look at it in simplicity, any variable whose outcome is uncertain based on some kind of probability, we are associating it to a random variable. Now this particular random variable, if it takes countable number of possibilities, Countable number, again, it could be limited, like a roll of a dice. The possibilities are only 6, 1, 2, 3, 4, 5, 6. Or it could be even unlimited, but still countable. It could be some hundreds, thousands, but okay, only numbers, only integers. They are still countable. So all those things, even if it is very few in number, a very small finite set, or even if it is infinite kind of a set, but as long as it is countable, we call that particular random variable as a discrete random variable. But on the other side, if the possibilities are completely uncountable, if the different outcomes are completely uncountable, probably if I look at the heights of the person, depending on the precision of measurement that I am using, any decimal value can come out. Probably if I am looking at it in centimeters, I could have 151, 152, or probably I can even go to 151.11, 151.12, or probably I can go even into a millimeters or micrometers and probably talk about a few more decimal points. Similarly, when I look at the rates of return, almost any number of values after the decimal point are possible. So what are the possibilities? I cannot literally count. Whereas if I am saying age in integers, it is still a discrete. Probably it can go right from 1 to 100 or 1 to 150 or whatever it is, depending on the minimum age to the maximum age. So it might be infinite, but it is still countable. So whichever the variables are more and more countable in nature, I call them as discrete. Whichever are uncountable, they are continuous. But sometimes in real world, what happens is, if the numbers are too large, we approximate it to a continuous. Numbers being too large, so which means in reality, probably creating a situation of continuous, creating a situation of discrete, there is a very thin line. Probably if I am talking about the stock prices, though almost any price is possible, probably the stock prices will increase in the rates of, let's say, 5 paisa. So though there are unlimited possibilities, but I can't get 151.08. So which means it's still a countable but a discrete, so a discrete set. But because so many values are possible, I may try to approximate it to a continuous. So that is the kind of a choice the user is having, whether he wants to use that particular variable as a continuous or a discrete. Because as the number of values increase, the discrete can be approximated to a continuous and vice versa. Probably a continuous can be taken in the form of a discrete, or a discrete can be taken in the form of a continuous, because at the end, for me, any distribution is nothing but it's a kind of a visualization of the possible frequency distributions. So generally, visualization of the possible frequency distributions of the future is what is coming out as a part of my understanding of a distribution. So it's a kind of a mathematical or modeling of the possible random possible outcomes that are going to come up in future, along with their associated probabilities. So that is what is typically coming out as a definition of a probability distribution. Now, when I look at a probability distribution, whenever I talk about a probability distribution, especially discrete or even continuous, whenever I use the word probability distribution, we actually define two important words here. One we call as probability function. The other we call as cumulative distribution function. Whether it is continuous or discrete, we have two different definitions or two different dimensions of any probability distribution. First, I look at a probability function, wherein I talk about what is the probability that any random value will take a value equal to x. So which means when I throw a dice, what is the probability that the random variable x, which is the value that comes up on the dice, is equal to 1? Or what is the probability that the random variable takes an even number? So this is what I'm calling as a probability function, where we are talking about the probability that the random variable takes a specific value. So this is generally represented by a simple small p of x. P of x is what we represent as probability that x equal to x. So this is called p of 1, probability that x equal to 1. But the same thing, when I take it in a continuous case, we don't use the word probability function, we use the word as probability density function. That's the only difference. The naming is different when I use continuous, but when I'm using discrete, I'm calling it as a probability function. And instead of p of x for a probability density function, we call it as f of x. And a few important things relating to this p of x, especially the discrete case. What I see is this p of x, just because it's a probability, it will lie between